Okay, our next term is beam non-uniformity rate, or what's known as the BNR. So the BNR describes how uniform, okay, the beam that is being created from the crystal, so thinking back to our piezoelectrical crystal, how uniform that beam is coming out. And we know that no crystal is perfect, and so no BNR is perfect, okay? So, the book goes into it being this ratio between the spatial peak intensity and the spatial average intensity. That's what the ratio means, but for our sense, it's really again talking about how that crystal is producing the beam and the fact that what we label on the machine, okay, as our intensity is the average that crystal is putting out at a given time. What's really happening is we get these peaks and valleys. And so in some places, we're going to have a beam, a little piece of that beam that's much higher than what we have set on the machine. And then there's going to be some places where that beam is going to be much lower than what we have set for our intensity. One thing to note, a BNR greater than 8.1 is not allowed on the market. It's considered unsafe. So let's talk about this. So again, it's the amount of variability within the beam, and it's measured in a ratio. So it's the highest intensity found in the beam relative to the average intensity of the transducer. So the average power and intensity over, so the power over the ERA of that crystal, compared to at where some point in that beam there's a peak, and how high is that peak? This should be BNR. So the BNR is the spatial peak intensity over the spatial average intensity, again, if you're doing that math. The ideal BNR is a 1-to-1, and that's not realistic. No crystal's perfect. So we don't have this place where the crystal is producing the entire beam the way, that's equal across. Typical BNRs tend to be 6-to-1. Newer machines have gotten better and are closer to 4-to-1. Again, this is something that has to be labeled on the machine or in the instruction manual of the machine. So those peaks and valleys, again, are due to the minute imperfections in the crystal. And so wherever we have these peaks, we're going to have places of higher intensity than what we have set for our average, okay? So this is what this looks like if you were to, blow it up. So the ideal, a 1-to-1, would be that the entire ERA of the crystal is producing the exact same amount of energy, okay? What really happens are these peaks and valleys. And so if we have our average intensity set on the machine as, 1.5, okay, that means all of this added together averages to 1.5. But somewhere in there, we have these peaks that are probably significantly higher than 1.5, and we have these peaks or these valleys that are significantly lower than 1.5. So what does that mean when we're thinking about this? So if we set the intensity at 1.5 watts per centimeter squared, but our machine has a BNR of 6-to-1, that means somewhere in this peak, right, somewhere in this beam, there is a peak that is at least 6 times higher than the intensity that we have set. So that means we can multiply that, right, 6 by 1.5, and somewhere we have a peak that is 9 watts per centimeter squared, okay? So the peak intensity somewhere in that is 9 watts per centimeter squared. The lower the BNR, the more even the intensity, and we have less concern about burning. As the BNR gets higher, so as that ratio number gets higher, we have more risk that we have these high peaks. And if what happens is if we kept the ultrasound head completely stable, okay, and just held it there, okay, the peak would be that one or a couple peaks that are higher than our average intensity would be hitting the same spots of the tissue and would be getting them much more power, much more intensity, much more energy, okay, than other areas. And that can actually be dangerous, okay? That can create burns. It can create what we call hot spots, which are areas of this increased intensity that feel very hot and burning to the patient. So this is one of the reasons, we'll have about 3 reasons that we keep the ultrasound head moving all the time. okay? And one of those is because we have these BNRs that aren't perfect, and we need to keep moving that average spatial intensity around so that those peaks keep moving around. Plus, think of it on the reverse side too. If we just kept stable, there are going to be areas coming off of that beam that are way below our intensity that we want. And so we would never raise those tissues directly below that intensity to the effects that we want. And so we move it around so that we get more of that average. Like I said, they have to have the BNR on the generators. So looking back at our example up here, we had 1.5 times 6, so that BNR of 6 equals a peak intensity of 9 watts per centimeter squared. Any intensity greater than 8 watts per centimeter squared, tissue damage can occur. So what this says is that somewhere in that peak, somewhere in this beam, we have a peak that would be potentially dangerous to our patient. So that's one of the reasons we keep that head moving, right? So that we don't let that peak sit in one spot too long, okay? But another thing we could do is if we altered our intensity, so if we dropped this down to say like 1.0, then we would only have a peak intensity somewhere of 6, which would keep us in that safe range no matter where that peak is. So the higher your BNR, the sometimes more limiting you can be on the strength of your intensity that you can increase. Because if we lower this intensity, we're going to end up having to increase our treatment time in order to get the same effects. So having a lower BNR can give you more flexibility in the intensities that you can set as well. Another term that's actually not in your book, but it's something that's coming out on newer machines all the time, is what's called the PAM BNR. And this is the peak area of the maximum BNR. So this just gives us a more accurate reading of that BNR. So again, with the BNR, we had these peaks and valleys, okay? And then we had the average spatial intensity that we end up setting. What the PAM BNR tells us is it actually maps out those peaks and valleys and shows us how much of the beam is producing those really high risky peaks. So the area of the crystal that produces those peak intensities. And we call it the beam profile. It's that map. It's essentially this picture. Okay. And so what the PAM BNR tells us then is if most of the area is producing, do we have a tiny peak here, or do we have a peak like this that's really large, but maybe not as high, right? So the peak intensity, the PAM BNR tells us a little bit more of how much that crystal is shooting off those high peaks and how much is shooting off lower. And so if we had a crystal that was a little more uniform, where yes, we have some peak intensity, but it's spread out, or it's only little individual peaks, we're less likely to have those issues with potentially burning. So only reason I bring this up is that more and more newer machines are going to be able to give you the beam profile and the PAM BNR, the peak area of the maximum of the BNR. And so I just want you aware of that.